So welcome to part 3 of lecture 31, where we've been talking about the adjoint. I apologize for part 2. I didn't realize I had left my camera on the whole time, so hopefully I didn't block everything, and you can download the notes and see all the information. So in this part, I just want to talk about the properties of the adjoint. So we've now seen that if you take two linear maps, or um, when you take their adjoints, you get linear maps going in the reverse direction. Okay, so what other properties do we have? Well, we have some other useful properties is that if you take s plus t and do the adjoint, it's the same thing as taking the adjoint of both of those linear maps and then adding them together. How does the adjoint respond to scaling a linear map? Well, that corresponds to taking the conjugate of the lambda, the complex conjugate, times the adjoint of t. If you take the adjoint of the adjoint, you will get back the original function. If you take the adjoint of the identity, you get the identity map in the reverse direction. And lastly, if you take a composition of functions, if you first do t and then do s and take the adjoint, that's the same thing as first taking the adjoint of s and then composing it with the adjoint of t. So this is for any t that goes from v to w, and s any linear map that goes from w to y. Okay. Now I'm not going to go through the proofs for all of these facts. Okay, you should go see the textbook. But the key fact is that you use over and over again. So you use the fact that whenever you see something like A, T star B, it's the same thing as TAB, because you're given information about T, and then you could use this map to turn this identity to turn it into properties about the adjoint. Okay. Okay, so if you stare at these properties for a second and you think about it, say if these were matrices, right? Where would you see these sorts of properties in terms of matrices? Okay, now this one here is really kind of intuitive, kind of instructive. Now the inverses of maps kind of satisfy this relationship, right? The order gets changed. But there's another property that you would have seen in Math 1OB that kind of observes this property where you take the product and then do an operation and then you change the order around. That operation is also the transpose. Okay, so what we're going to be doing next is actually defining what's called the conjugate transpose. So it's actually a little bit more general than what you would have seen in Math 1B03. And the way that the conjugate transpose of a matrix is formed, okay, and we call it A star here, it's the matrix formed by taking the transpose of A and then the complex conjugate of each element, okay, inside of the matrix. So this is probably one of these definitions where it's a little bit easier to describe in terms of an example. So let's do that. Okay, so I have my example over here. So here I have a 2 by 3 matrix and I want to figure out the complex conjugate. Well, I just take the conjugate, so I take each row and it becomes each column, but as I rewrite it, I take the complex conjugate of each element, right? So 2 minus I is the conjugate, complex conjugate of 2 plus I. The complex conjugate of minus 7i is 7i, 0, 1 plus I. Okay, and why is this kind of in some ways a generalization of taking the transpose? Well, if all the entries of A are real, then the complex conjugate is simply the transpose of the matrix A. Okay. So if you haven't been fully understanding kind of what's been going on with respect to the adjoint, and I agree that at the first time you see this is a kind of a new complicated definition. Here's a better way maybe to think about it, what this theorem does. It kind of helps us understand what's going on. Okay, so first of all, I'll state this theorem and then the observation. So let's say you take a linear map and you have an orthonormal basis for the V and you have an orthonormal basis for the W. And you can look at the adjoint, and you can figure out what the matrix of that adjoint is associated to the bases F1 through Fm, because remember we're turning the order around with respect to the bases E1 through Em. What is the relationship with the original matrix, right? So this is the matrix associated to these two bases. So this is kind of like the given information, but you take the conjugate, complex conjugate of it. Okay, so remember there's two things over here. Okay, oh, and actually I'll explain it a little bit right below here in terms of this observation. Okay, and this may help you a lot to understand what we're doing with the adjoint. So if we use the standard basis of Fn and Fm, what this is saying is that the matrix of the adjoint is the matrix you get by taking the complex conjugate of the original matrix, right? So this is the conjugate transpose, the conjugate transpose of MT, and over here, this is the matrix of the adjoint. Okay, so I'll say a little bit more when we come back about this in the next part, but we'll also verify this particular fact.